All right, let's record this 60-second summary for the short form edit. Welcome to the AI Paper Podcasts. Today's paper is Learning to Foresee, Unveiling the Unlocking Efficiency of On-Policy Distillation by Yuchen Kai and colleagues, published May 13th, 2026.
Yeah, let's get right into it.
So if you're working with large language models, here is the absolute bottom line. We know on-policy distillation, or OPD, is vastly faster than reinforcement learning for post-training.
Right, definitely.
But until now, we haven't actually understood the parameter-level mechanics of why. Well, this paper proves OPD possesses this sort of mathematical foresight.
Exactly.
It figures out the final optimal parameter update direction incredibly early in the training run. And by identifying this, the researchers built FOPD, which is this plug-and-play method that literally extrapolates along that early update trajectory. It speeds up post-training by 3x with 0 extra trainable parameters.
Yeah, to synthesize that for the technical audience here, it's basically, instead of blindly exploring a massive high-dimensional parameter space like RL does, OPD collapses into this strict low-rank subspace almost immediately.
Wow.
And FOPD just calculates that trajectory and hits the fast-forward button, totally bypassing the compute-heavy optimization loop.
All right, and that's the short-form summary wrapped up. So now let's unpack the actual mechanics of this foresight for those of you dealing with these massive training runs.
Yeah, it's a big deal if you're paying for the compute.
Oh, absolutely. So the paper identifies 2 distinct levels where this foresight occurs, right? And the first one is the module allocation level.
Right, where the updates are actually happening structurally.
Exactly.
Yeah.
So to understand this, let's step away from the generic, finding a peak on a mountain analogy. Let's look at what's actually happening to model's architecture.
Okay.
Imagine tuning a massive, a 10,000 band audio equalizer to perfectly replicate a specific master track.
That's a lot of dials.
Right. So traditional reinforcement learning is like trying to tune it by ear, just randomly sliding every single dial up and down, checking if the song sounds slightly better, and adjusting again.
High variance.
Exactly. It's incredibly high variance, and you're touching a lot of dials that just do not matter at all.
Yeah, that captures the structural redundancy of RL perfectly, honestly. Because when you have a sparse reward signal, like, say, a simple pass or fail at the end of a really long math problem.
Right, they got a benchmark.
Yeah. The credit assignment problem just becomes chaotic. The optimization process has to distribute updates across the entire network because it doesn't explicitly know which specific layer was responsible for getting the final answer right.
So it just tweaks everything.
Right. It tweaks everything. It's sliding the drum dials even when the drums sound totally fine.
But OPD is different because of the teacher model.
Exactly. Because it uses dense token-level supervision from a powerful teacher model, it's like being handed the actual sheet music.
Oh, I like that.
You immediately see that you only need to adjust, say, the string and brass sections. You just leave the drums alone.
The paper actually calls this property functional redundancy avoidance, right?
Yes. So under the hood, that dense supervisory signal is acting as a ruthless structural filter. OPD naturally identifies regions of the model that have, really low marginal utility for the specific reasoning task.
It just ignores them.
Pretty much. It basically zeroes out their update momentum. It concentrates the parameter updates purely on the modules that are actually critical.
The ablation studies on the MATS 500 benchmark in the paper really drive this home for me, because they took models like Quen38B and they tracked the update norms, which is essentially measuring how much the weights were changing in each individual layer.
Right, the actual magnitude of the change.
Yeah. And in OPD, the embedding layers receive almost 0 update norm.
Which is wild.
It is. In fact, the researchers found you can completely freeze the embedding layers, or even swap them back to the base model's raw embeddings, and the final reasoning accuracy barely flinches.
I mean, mathematically, it makes perfect sense, though.
Why is that?
Well, if you're distilling reasoning capabilities, the mapping of raw text to the initial vector space, which is the whole job of the embedding layer that's already highly optimized from pre-training.
Oh, right. It already knows English.
Exactly. The gap between the student and the teacher isn't in how they perceive vocabulary. It's entirely localized in the deep relational logic, which is handled by the MLPs and the attention heads.
So OPD just recognizes that localized need instantly.
Instantly. But the crazy thing is, if you try freezing those same embedding layers during an RL run,
Performance drops.
performance tanks. The RL process is just so chaotic that it has already tangled up its reasoning pathways across all those redundant parameters.
So if you lock them down...
You break the fragile reasoning chain that RL just spent thousands of steps building.
Wow, so the supervision itself is doing architectural routing without us having to explicitly write, like, a routing algorithm. We are naturally pruning the update space. But, narrowing down where the updates happen is really only the first part of this whole phenomenon.
Right, we have to look inside those layers.
Yeah, let's look at the actual geometry of the updates within those critical MLP and attention layers. Because is the optimizer still taking a chaotic, winding path, just restricted to a smaller set of layers?
No, not at all. And this is what brings us to the second major property they found, which is the early low-rank lock-in.
The update direction level.
Exactly. This is where we analyze the spectral concentration of the update matrix, which they represent as delta W. When the researchers actually mapped out the trajectory of these parameter changes, they found that OPD's updates are highly concentrated in a very low-dimensional subspace.
We should probably define what that looks like visually, because I found the TSNE plots in the paper to be pretty striking.
Yeah, they really are.
And for those listening, TSNE is a technique used to compress, tens of thousands of dimensions down to a 2D plot, just so our human eyes can comprehend it. If you trace the RL trajectory from the base model checkpoint to the fully trained final model, it literally looks like a drunk walk.
It's all over the place.
It spirals, it meanders around dead ends, it just slowly drifts toward the goal. But the OPD trajectory is a razor-straight line from the origin directly to the destination.
The visual is stark, but honestly, the cosine similarity metrics are what prove it empirically.
Let's get into those numbers.
So cosine similarity in this context measures the angle between two vectors, right? They took the top singular directions of the update matrix at intermediate checkpoints, say just 10 or 20% of the way through the training run. And they compared them to the ultimate update matrix of the fully trained model.
So they're basically asking, at step 1000, is the model already aiming in the exact same mathematical direction it will eventually reach at step 10,000?
Yes, exactly. And for OPD, that cosine similarity hits roughly 0.8 or 0.9 within the very first fraction of the training run.
That's incredibly high.
It is. The top singular directions have already aligned almost perfectly with the final destination. The optimization trajectory just locks in immediately.
And how does RL compare there?
RL shows a very slow, shallow, linear climb in cosine similarity. It requires that entire massive exploration phase just to slowly orient its subspace toward the target.
Man, if you're an ML engineer spinning up a cluster today, that metric alone should make you stop and rethink your entire pipeline.
Oh, absolutely.
Because if the model mathematically knows the correct update direction within the first, 15 to 20% of the training loop?
Yeah, early on.
Then why are we paying for the GPU hours to run the remaining 80%? If the trajectory is a straight line, why walk it step by step?
Exactly.
Can't we just take that early directional vector and extrapolate it, stretch it out?
And that is the pivotal question of the entire research, and it leads directly to the algorithm they propose, FOPD.
Right, let's talk about FPD.
By proving that subsequent training in OPD is primarily just accumulating magnitude along an already established direction, rather than making nonlinear adjustments to the direction itself. The authors realized you can bypass the optimization loop entirely.
Okay, let's break down how this plug-and-play extrapolation actually works in practice. Because FOPD doesn't require injecting new adapter modules or tuning a complex set of hyperparameters.
No, it's surprisingly elegant.
You just run your standard OPD training, but you stop it at an early checkpoint. Let's call the difference between your base weights and this early checkpoint, delta W early.
Okay.
You take that matrix and you scale it by a factor, which the paper calls beta.
Right. And the math behind determining that beta factor relies on estimating the expected final norm of the weights.
How do they do that?
You look at the rate of change of the Frobenius norm, which, just for context, is effectively a measure of the overall magnitude of the weight matrix. So you look at how that changes between step 0 and your early checkpoint. You can mathematically fit a curve to that growth to predict exactly where the norm would naturally plateau if you just let the training run to completion.
Oh, I see.
And that difference dictates your scaling factor. You are artificially completing the trajectory.
But there have to be physical limits to this, right? I'm playing devil's advocate here for you guys. If I have a vector pointing in the right direction, Why not just push beta to 1.5 or 2.0 and create a model that's twice as good as the teacher?
Right, the more is better trap.
Yeah.
Because you would overshoot the target latent representation entirely.
Oh, it breaks.
Yeah. The paper shows that optimal performance is actually tightly bounded when the scaling factor beta is between 0.8 and 1.2.
Okay, that's a pretty narrow window.
It is. Remember, distillation is all about matching the teacher's behavioral distribution. NKL divergence is the metric we use to measure how much the student's probability distribution differs from the teacher's.
Yeah.
When you apply the FOPD extrapolation within that 0.8 to 1.2 sweet spot, the KL divergence just plummets.
So the student perfectly aligns with the teacher, snaps into place.
Exactly, it snaps into place. But if you push beta to, say, 1.5, the KL divergence explodes, you're pushing the weights past the teacher's logic.
What happens to the model then?
The model's reasoning becomes overly rigid, it starts hallucinating, and it just loses the nuanced probability distribution it was supposed to inherit. The linear extrapolation only works if you land exactly within the teacher's target distribution subspace.
That makes total sense. And the results validating this are incredibly robust, which is great to see.
Yeah, this isn't just toy model stuff.
No, they applied FOPD to Quen 2.5, Quen 3 architectures, up to 14 billion parameters, mind you, and DeepSeek models.
Serious scale.
Very serious. They ran it against highly complex reasoning datasets like MAD 500 and various coding benchmarks. And the outcome? An average training acceleration of 3x.
3 times faster.
You get a fully post-trained reasoning model in a third of the time, maintaining final performance that is statistically comparable to a full-length standard OPD run.
It's a massive efficiency gain, mainly because it exploits the inherent geometry of the distillation process.
Right.
Instead of trying to force efficiency through heavy architectural modifications like pruning or quantization, it simply leverages the physics of the optimization landscape.
It's working with the model, not against it.
Precisely. It realizes the model is walking down a straight, well-lit hallway and just decides to teleport to the end of the hall.
I love that. But, AI researchers tuning in right now, they need to know why the math actually allows this.
Here, the underlying theory.
Yeah. We know the model collapses into this predictable low-rank trajectory, but what are the underlying physics forcing it to do so? Because the appendix of this paper dives deep into the information theoretic and local curvature perspectives, and we definitely need to unpack that.
Oh, absolutely.
Like, why doesn't standard RL have this straight line geometry?
Well, it fundamentally comes down to implicit compression.
Okay.
In RL, the model is engaging in a high-entropy search. The landscape is foggy, so to speak, so the optimizer sends probes out in thousands of dimensions simultaneously.
Right, trying to find the signal.
But in OPD, the dense supervision from the teacher provides a highly structured target from step 1. This structure forces an implicit low-rank bias onto the optimization dynamics.
Interesting.
So the student model isn't actually searching, it's compressing the teacher's latent representations into its own weights.
The authors use the eigenvalues of the Hessian matrix to explain this local curvature, right?
Yes, they do.
Let's make sure we ground that concept for everyone. The Hessian is essentially a mathematical way to measure the curvature or the steepness of our optimization landscape.
Correct.
So if we imagine our parameter space as a physical terrain, what does the Hessian tell us about the OPD environment?
All right, so if you calculate the Hessian for an OPD update step, you're looking at the driving term, which is the projection of the teacher-student residual. The researchers found a massive spectral gap in these eigenvalues. Now, going back to our terrain analogy, a spectral gap means, though, in a few very specific directions, the landscape features incredibly steep, towering canyon walls.
Okay, huge walls.
But in the thousands of other dimensions, the landscape is just a completely flat valley.
Oh, wow. So the gradient, the force that's pushing our parameters toward the solution, it just gets immediately trapped in this narrow, steep canyon.
Exactly. The gradient isn't pushing the parameters in all directions because those flat dimensions offer no leverage whatsoever. It's almost entirely pushing them along those few principal axes defined by the steep canyon walls.
That makes perfect visual sense.
Right. And this provides a rigorous mathematical proof for the early low-rank lock-in. The optimization is confined to a dominant subspace right from the start because the local curvature of the loss landscape demands it.
And this perfectly ties back to our first point about avoiding redundant layers like the embeddings.
Yes, it does.
If an embedding layer has negligible coupling with the teacher's residual, meaning, the teacher isn't asking the student to change how it represents a comma or the word the, then its driving term in the Hessian is near zero.
Exactly zero, effectively.
So the canyon walls for those parameters are totally flat, so the optimizer just leaves them alone.
Which demonstrates that OPD isn't just reinforcement learning with better labels.
Right.
That's a really macroscopic, slightly outdated way of viewing post-training. This research proves that dense supervision fundamentally alters the actual optimization geometry.
It changes the shape of the space itself.
Yeah. It creates a space that is incredibly compact, stable, and completely devoid of that high variance noise that plagues RL trajectories.
And this is exactly why a simple linear extrapolation like FOPD is even mathematically possible in the first place.
Right.
If the lost landscape was highly non-convex, full of chaotic bumps, spiraling switchbacks, and localized traps, a linear stretch would just throw your model off a cliff into absolute garbage parameter space.
You'd extrapolate right into a wall.
Exactly. But because the space is locally flat and driven by this dominant straight canyon, you can scale the vector and land safely at the destination.
But, and this is important, we do need to address the limitations of this geometric assumption before we wrap up.
Yeah, let's play fair.
The authors are very transparent that their proof relies on a local linearization of the OPD dynamics.
Meaning what, practically?
They are characterizing the behavior in a neighborhood relatively close to the base model.
So this works flawlessly when the student base model is already highly capable. Like an 8B model that has seen trillions of tokens of pre-training and just needs its specific reasoning style aligned to the teacher.
Right. It doesn't have to travel a massive distance in parameter space.
Okay, that makes sense.
And furthermore, while this is thoroughly validated on dense math and code reasoning tasks, it hasn't been stress tested against massive distributional shifts.
Like what?
Think about complex multi-turn agent environments where a model has to interact with external tools, or multimodal reasoning where visual encoders are constantly shifting the context.
Oh, right.
In those scenarios, the structure of the teacher-student residual becomes vastly more complicated.
The canyon might not be perfectly straight anymore.
Exactly.
If the task is highly conditional and multi-turn, the landscape might develop switchbacks. And if that happens, a simple 3x linear extrapolation might overshoot the curve.
You might need multiple waypoints or like an adaptive scaling approach rather than just a single fast-forward button.
It's a critical area for future research, definitely. But for the vast majority of standard reasoning distillation workloads being executed today, this local linearization seems to hold true. And the efficiency gains are just undeniable.
Oh, absolutely undeniable.
Which brings me to a final implication of this research that you, as the listener, really need to think about.
This is the big picture stuff.
Yeah. We just spent this deep dive detailing how dense teacher supervision permanently locks a model into an incredibly narrow, low-rank update subspace within the very first few steps of a post-training run.
Right.
And the remainder of the entire compute cycle is literally just scaling the magnitude of those weights down a preordained path.
It really forces us to question the underlying architecture we're actually training.
It absolutely does. If the optimizer mathematically locks onto the correct reasoning path on day one, does this imply that the vast majority of the parameters in our multi-billion parameter large language models are structurally redundant for advanced reasoning?
It's a provocative thought.
We are spinning up massive GPU clusters, burning millions of dollars in compute to search through hundreds of billions of dimensions just to find tiny, highly compressible mathematical paths that the optimizer actually found in the first 100 steps.
Well, the information theoretic perspective suggests exactly that. Our current dense architectures are vastly overparameterized for the actual latent logic they're performing during these reasoning tasks.
We are essentially paying a massive exploration tax.
I like that phrase.
We're paying for the model to slowly step through 100 billion dimensional space because we don't currently have network architectures or initialization algorithms that can natively spawn inside these low-rank subspaces.
Right, we have to find them first.
FOPD is incredible because it cuts that exploration tax by a factor of 3. But the underlying physics proven in this paper suggest that the tax shouldn't even exist in the first place.
The model possesses the foresight automatically.
Yes. We just need to stop forcing it to walk the entire path manually. Definitely something to think about the next time you authorize a massive post-training compute budget.
Absolutely.
And that is it for today's deep dive. Make sure to subscribe to AI Paper Podcasts for more breakdowns of the research pushing the boundaries of machine learning. See you next time.